Welcome back to Mr. Brown's Basement. In this video, I'm going to finish off the repair of my Sylvania Halolight 21C509 television. Since YouTube has recently leaned heavily into YouTube Shorts, they've been pressuring creators to significantly increase the length of their regular videos. I'm sure there are many reasons, but I'm guessing it's mostly so YouTube can insert more ads throughout the video. I don't allow mid-roll ads to interrupt my videos, but I can't stop pre-roll ads. This is my first video, which I deliberately made longer rather than break it into shorter segments. Please let me know in the comments whether you prefer this longer format, or if you'd rather watch 10 to 15 minute videos on my channel.
Thank you very much. And now we return you to our regular scheduled program in progress.
Since the last video, I've finished recapping this chassis entirely. All the capacitors are done, and you can see there are quite a number of them. Of the 90 or so resistors, about 50% of them, or 45, were out of tolerance. I also redid the sync separator section, which was right around here. And yes, there are quite a number of bad resistors there. So now that the main chassis has been done, the next thing is to look at the section which has the tuner and the front-facing controls. This is the control assembly for the television. If you didn't see the first couple of videos, then you might not have seen this before.
These 6 shafts and 2 sliding arms poke through holes in the panel.
This is above the CRT, so the picture tube is below this. And the chassis stands vertically about here, underneath this. This plugs into the chassis with these plugs over here. There's a nice secure ground. This connects all the controls together, and this is from the tuner. Potentiometers, and there are a couple capacitors here and a couple resistors that need to be checked. This assembly over here, which changes the channel, this I have to do something about. What there should be is a string that turns the tuner every time this is snapped back. And yeah, there's another resistor over there. Let's look at the other side. This is a typical wafer style tuner. This is a selector switch with coils corresponding to each channel. And there's a set of contacts from each wafer for each channel. This kind of wafer tuner is not fun to fix. In fact, usually when you take it apart, you make things worse. And I would only take it apart if there were absolutely no other options, like if it was already messed up. There are some resistors inside. You can see 100 kilo ohm right there and what looks like a 33 kilo ohm over there. I'm going to test them if I can. I don't know whether I could replace them if I had to. I hopefully won't have to replace them. Back in the day, you sent your tuner away to a service that rebuilt the tuner. I don't know anything about how it was done. They probably replaced large sections of it. That will have to be cleaned. The controls on the other side will also have to be cleaned and lubricated. Let me get to replacing these capacitors first and testing the resistors and testing the switch too. It's a terrible shame that the channel indicator is not illuminated. I don't think I'm going to do anything about that. I'm going to keep it original. I've got the ohmmeter set up on the on-off switch, and guess what? The on-off switch is bad. It's something I see all the time on Predictas, but I was not expecting to see it here. It's possible that the switch is just really dirty. I don't know if this can be disassembled. It's also possible the contacts are completely burned out. Hard to say, but it's definitely not working. Yeah, this needs some lubrication too, but that's beside the point. It's not changing. Yeah, bad switch. I've sprayed contact cleaner, this stuff, into the switch, and beginning to do something. So it's just very dirty. I may just have to continue working it. But it is showing signs of life, which is quite a relief. Contact cleaner doesn't always work miracles, but this time it has. This is just a 6-volt bulb connected up to a power supply through the switch. So yeah, it works. That's a relief. I don't know whether it was the contact cleaner or just working it so that the friction inside the switch cleaned the contacts, but it's working. For the controls, you don't use contact cleaner, not unless you want to destroy them. Instead, you use fader cleaner and spray it in there so that the resistance element gets soaked with the cleaner, and then you work the control. And that will smooth out any defects in the element. They've all been sprayed. The one labeled fringe sounded a little rough. Sounds a bit better now. From what I can tell, this spring over here hooks into the back of the wheel there, which is where I have it. And this end of the spring here is supposed to hook into this piece of arborite. And as you see, it has completely failed. So what I need to do is glue in a piece of material that's going to hold this end of the spring. It's not going to take very much. This is phenolic perf board used for mounting electronic components. I cut a small piece. What I'm thinking of is gluing this piece in around there somewhere. And yes, the spring will fit through. I epoxy it right there. There's enough surface area that it should not come apart. While the epoxy is drying on this board, I'm going to apply lubricant to all the moving parts, like over here in the fine tuning section, over there. I'm most interested in making the mechanism move smoothly so that there's less of a chance of binding and something breaking. I'm going to clean the contacts like this, and then once they're all clean, work the tuner. Friction between the contacts and the brushes that touch them will clean the contacts. You don't want to use anything like sandpaper at all. Yeah, just a little bit of dirt and dust. I think it's supposed to operate this way. Look at the threading of the belt. If that belt ever breaks, it'll be a disaster. Okay, the spring goes in there and it goes into one hole in the wheel. And the string goes over the wheel. If I want to advance it one channel, if I want to advance it a couple channels, or 3 channels. I'm finding that with that hook over here, it tends to come out of this groove. With it over here, it seems to be more reliable, but the spring never completely relaxed. Is that a bad thing? I guess not. Sam's PhotoFACTS doesn't have any dial string diagram at all.
It works reliably, but is this the way the manufacturer designed it? I don't know.
We're getting very close to the point where I apply power. Some people would call that the smoke test. Hopefully there's no smoke. I've got the main chassis over here, but I've also got this sub-chassis with the controls on it that has to be hooked up because it has not only all the controls, but also the on-off switch and the tuner. All has to be wired together. My workbench is struggling to find space. Since my last video, I've added some NTC thermistors. It will reduce the power on surge, make it less likely that a filament gets blown when it's first powered up. What I have to do next is put in the tubes. I'll get out my isolation transformer. I'd like to have this isolated from the line because it's a hot chassis. Everything here is connected to one side of the line. I could zap myself quite badly if I touched something here and something grounded. I'll have to put a dummy resistor into the CRT socket, because that's part of the filament string. They're all wired in series, so if one tube is out, including the picture tube, it won't power up. I'm not going to plug in the deflection yoke. In this set, it's actually quite well designed. If the yoke is not plugged in, power to the horizontal output and the vertical output tubes is disabled, which means there will be absolutely no high voltage. Later on, if everything goes well, then I'll plug in the yoke and see if I've got high voltage and how much high voltage I actually have.
I'm ready to start testing. I've connected a 10 ohm 5 watt power resistor to pins 1 and 12 of the CRT socket to complete the circuit for the filaments. The deflection yoke is disconnected. What I should see is the filaments heating. I will probably hear the horizontal and vertical oscillators running, and when I connect up a speaker, I should also hear hum and or hiss through it. I shouldn't smell anything except possibly hot tubes. Meanwhile, I'll have a voltmeter on the B+, which in this set should be 260 volts with 120 volts AC in. Since this TV has silicon rectifiers instead of a tube rectifier, I expect the voltage to come up right away and not wait for the filaments to heat. As the filaments heat, I expect the B+ to sag as the tubes begin to conduct.
What I don't want to see is smoke or arcing. Doesn't usually happen, but it happens to the best of us. Yeah, I know I need a bigger workbench, but that's not going to happen anytime soon, so I'll make do with what I've got. The variac plugs into the wall, actually into the power strip. Isolation transformer plugs into the variac, and the TV plugs into the isolation transformer. I'm about halfway there with at about 170 volts on B+, I guess. About half the voltage for the filaments. The filaments are beginning to light. I'm getting a little bit out of the speaker. I'm not hearing any oscillators yet. All the tubes are lighting. I've got the volume turned down, but if I turn it up, so that's a good sign. Hiss. Now I need to hook up a picture tube. Let's kill it and get that hooked up. I'll be using this Telecheck black and white CRT test jig, which is basically a CRT in a box with the yoke. So I connect it up to the yoke. I connect it up to high voltage anode connector, and I connect it up to the CRT socket. So if I didn't have a complete mess before, I certainly have a complete mess now. So let's power it up again. I didn't get a chance to capture this on video, so I'll describe it. I was increasing the voltage and not getting anything on the picture tube at all. Voltage seemed to be a little bit low.
With around 80 or 90 volts AC going in, and with B+ around 200 volts, B+ started decreasing. That shouldn't happen. Then the fuse tripped. Let's repeat that one more time just to make sure it wasn't a fluke, like a defective fuse.
Okay, one more try. I've put a new fuse in. I've replaced the damper tube. The high voltage cage is off. I wouldn't do this in a color set, but in a black and white set, it's only going to be 14 or 15 or 16 kilovolts, no x-rays at those voltages. But I'm certainly not going to get in there with my fingers. Everything looks good. Yep. Everything looks good. All right. Okay, we are at just shy of 100 volts. Okay, the input voltage is about just under 40 volts. $52 volts going in. Heater's beginning to light. 160, 70. Okay, I'm getting some humming. Okay, voltage is decreasing. But we're at, okay, 135, it's increasing now. We've got 65 roughly going in, B plus at almost 150. High voltage tubes are lighting, but it's still way too low to get a picture. Way too low. Brightness is all the way up. Yep, nothing. Okay. 160. Going down a little bit. It is going down. I have a funny feeling we're going to blow the fuse again. I'm willing to spend a fuse on that. 133 volts. $128 volts. Hard to say. I got 65 volts going in, B plus 127. Yeah, that would be about right. Okay. Probably all the tubes are conducting now. Okay. Bring it up. $136, $135. Yep, it blew. And now the voltage is up to 204.
Let's see what must be going on. I've illustrated the path that B plus follows to the fuse in orange. The path in blue should be at B plus potential, but because the fuse tripped, we know it can't be. It's probably being shorted close to ground. There's not much that could be doing it. It's capacitor C102, choke L16, and possibly the anode of the damper. It's the screen grid of the horizontal output tube through resistors R110 and R111 and C101 and possibly R109. That's it. I replaced R109 and R110 and 111 tested okay. When recapping, I replaced C101 and C102. There must be a problem at or near one of these components. I tested all the tubes, and unless I missed a shorted tube, unlikely, it can't be a tube. It must be a defective or incorrect component, or, more likely, a wiring error at a terminal strip or the tube socket where one of these components sits.
There was a small wire bridging from here to here, and that is the horizontal frequency coil, which definitely should not be shunted. Maybe that's not the only problem, but that was a problem. I've cut it off. I don't even know how that happened.
One other short circuit was discovered in the B+ line near the yoke socket. Let's try again with the short circuits removed. I've got the VN around 100, set to about 100 volts. We'll see if it has to be adjusted. Okay, voltage goes straight up to 260, but it's going to decrease slightly as the tubes warm up. They start drawing current, and there's more voltage drop across the power supply resistors. That's normal. I hear the horizontal oscillator. I've disconnected one of the windings, and I'm going to see if I get, ooh, I'm getting quite a sound. There's nothing on the screen. Nope. Yeah, I have a funny feeling it doesn't like this test jig. Let's try it with its own CRT and yoke. Well, after adjusting the horizontal oscillator, which must have been really far out, I'm getting this. It's actually looking better in reality than it does through the camera lens. Let me see if I can hook up a signal generator to it. There's my crosshatch pattern. Adjusted vertical linearity, and it's not too bad. I just have to shift the picture over. I'll try a regular video signal, like a DVD player, see how that looks. After some adjusting, I haven't got a bad picture, considering that this set hasn't been aligned. Adjusted the vertical height and linearity and width. It seems that it takes a fair amount of overscan to get it to fill the picture. I'm wondering if perhaps one of my output tubes is a little weak. Nevertheless, I'm really not disappointed by this so far. This is a very decent picture on a set that has just been recapped and had its resistors replaced. Really nothing else. There's a dark region at the top of the screen. I think that's letterboxing of the DVD movie I'm playing because it doesn't show up in the DVD menu. But that dark region should be level, and it isn't. I'll have to loosen the deflection yoke and turn it a few degrees to straighten out the raster. Some TVs have raster centering magnets near or on the yoke. There is noise in this picture, and that's courtesy of the RF modulator I'm using. Just to make life interesting, I've discovered that the antenna terminals for the VHF tuner have been stripped. So somebody at some point over-tightened these, and now they can't be tightened at all. I tried attaching a matching transformer to it, and it wouldn't stay because they can't be tightened. I don't have an exact one of these, but I may have something which can be adapted. I want to be able to attach a matching transformer or an antenna at the very least. I think the simplest solution for this will be to desolder the resistors where they meet the terminals, pry them out, and then put this in on top and then glue it in place. It might not win any beauty contests because of course it's brown, it's black, but I don't think that's very important. That's the terminal. And that's the board without the terminals. No one will know that this is not OEM, except everyone who watches this video. One of the features of the Halolight was that you were supposed to be able to remove this glass to clean it. I have to remove this glass to get to the Halolight tube, and I can't yet see any obvious way to do it. Maybe my Halolight is an exception. This piece is captive and doesn't want to leave, even with those 3 screws out. Maybe I'm going to have to take off this bezel again and lift it up and out. This screw and that screw should allow the glass to come out. Maybe with this model it was never intended that the average housewife could clean the glass. Yes, that worked. That allowed the glass to come out. Now the translucent bezel should come out too. And it is out. And there you can see in its glory the Halolight tube. So it's a fluorescent tube made in the USA, which is shaped like the screen. I want to take it out without breaking it if I can, and then I can worry about replacement. If you didn't see the earlier videos, you didn't see that I tested this, and it does not work. This is 12-volt LED strip. It's RGBW, or red, green, blue, white. The color of white is 4000K. I'll be using the white LEDs for sure. I may need the blue LEDs to tint the color closer to the color of the picture tube's P4 phosphor. We'll see. This strip is common anode, so all the positive lines are connected to one common wire, and there are separate wires for the red, green, blue, and white cathodes. It's self-adhesive and should be able to substitute for the dead Halolight tube, which is virtually impossible to replace. It doesn't look like the LED strip will neatly affix to the tube, so I think I'm going to end up destroying the tube. It's not really worth spending all the time and care to try and release these clips. I did try squeezing them. They didn't come out. And these up here are not going to be easy to squeeze. They'll probably end up breaking the tube anyways. I think I might as well just do it. I don't like breaking fluorescent tubes, but in this case, it's probably the easiest solution. The LED strip is in. It's roughly along the same path as the original tube. To the extent possible, of course. I'm going to put in the diffuser and see how it looks. This is with 12 volts. I'd never run it at 12 volts. Not bad. Let me turn off the light. That's certainly a luminous frame. This is 4000K, but that diffuser makes it much, much warmer. I think adding a little bit of blue should make it more realistic. Before going any further, put some silicone on to make sure the adhesive never fails if it gets heat from the CRT. Here's the Halolight power supply. This would have powered the fluorescent tube, which was around the screen. In it was, and I'm saying was because it's dead, this 800-volt transformer and a bunch of voltage divider resistors. That's why they're so big. And a selector switch, which pokes through the back of the cabinet. And I want to reuse it because I'd like to keep it looking as original as possible. The switch they employed was a 2-gang, 4-position, shorting rotary switch. One gang was used as an on-off switch for the Halolight on the transformer's primary side. The other gang was used to choose which resistors were in the circuit in order to dim the Halolight on the transformer's secondary side. Here's a diagram of a shorting rotary switch, sometimes called a make-before-break switch. This switch is ideal for this application, and I'm going to reuse it. It's easier if I try to explain how they use the switch than trying to understand the schematic. As it was from the factory, the right-hand gang was wired so there was no continuity in the first position, but continuity in positions 2, 3, and 4. Hence, it served as an off, on switch. And I'm going to be doing the same with it. The left gang was used to select which power resistors were in series with the Halolight tube for low, medium, and high brightness. Since I'll be using a solid-state solution to drive the LED strip, my circuit is going to be different. I'll be using this transformer, 12 volts at 450 milliamps, which is plenty. And don't worry, I'll share the schematic later on. Unlike the original circuit that used voltage divider resistors to directly control the brightness of the Halolight tube, I'll be using an adjustable 3-terminal voltage regulator to control the brightness of the LEDs. The way the voltage is controlled on this regulator is by choosing values of resistors R1 and R2 to deliver a particular voltage to the V-adjust terminal of the regulator. R1 is typically 240 ohms. R2 will determine the output voltage that can be set from about 1¼ volts to about 2.5 volts below the input voltage. Note that if the V-adjust terminal is allowed to float, the entire input voltage will be on the output, which is a situation which must never be allowed to happen, as it will cause the LED strip to draw enough current to self-destruct. Through experimentation, I determined that voltages of 10.4, 10.7, and 11 volts to the LEDs for low, medium, and high brightness would be ideal. I designed the circuit so that the shorting rotary switch would add resistors in parallel with a base brightness value of R2. Doing it this way means that if the rotary switch ever becomes dirty, makes poor contact, or fails completely, the voltage delivered to the LEDs will be the minimum and not the entire input voltage. After connecting my hand-picked resistors to the selector switch, all my measurement voltages were between 0.1 and 0.2 volts too high. While this doesn't sound like much, I could see the difference. Particularly in the high brightness setting, the Halolight effect looked brighter than the CRT, and that's no good. To compensate for the resistors being slightly off, I added an additional 100K resistor in parallel with R2. This brought all voltages within 0.05 volts of the target values, and it looks real good.
Here's the Halolight power supply, all finished. I drilled one hole there for the regulator, which as you see is bolted on. Over here is one other hole which holds a full-wave bridge rectifier on that side, and a terminal strip which gave me 4 extra tie points on this side. On the terminal strip, I mounted the 2 capacitors, the diode, R1, which is one of the 2 resistors that determine the output voltage of the regulator. Over here is R2, 1.88K. Using this switch, it adds these 2 51 kilo ohm resistors in parallel for low and medium settings. This is just a 100 kilo ohm resistor just to trim it to the voltages that I wanted.
Here is the schematic. The single most expensive item is the step-down transformer. For ease of mounting, I used a 4-amp full-wave bridge rectifier with a mounting hole. I also used a regulator in a TO220 package because I could use the mounting bracket as a heatsink. There is no need to electrically isolate the regulator from the bracket. In the worst case, the regulator dissipates about 1.5 watts, so bolting it to the mounting bracket is optional. I would recommend it though. Here's an updated view inside the set. You can see the Halolight transformer at the top, the brightness selector switch on the left. That's what it looks like. Hell of a lot better than it did when I got it. Not only is it cleaner, but the CRT is not dying to fall out. The Halolight circuit has been finished and reinstalled. Here goes. Never can remember which way to push it. Don't know why I did that. Looks sort of purple on the camera. Ooh, okay. It's not purple, it looks blue in reality, and on the camera it looks purple though. Actually, it looks like a very good match. Not through the camera though. That's at the lowest brightness. That's weird that it flashed green. Let's see what happens when I turn it off. Okay. No Halolight? What's causing the flickering problem is this section over here, which turns on and off the transformer. These contacts may be dirty or worn. This set of contacts does the dimming, and it seems like they're okay. I'll use some of this stuff and then work the control, and that should clean it up. If these contacts are worn, that wouldn't totally surprise me. It happens in 60-year-old TVs. There were a couple spots on the cabinet, like here and here, that the veneer had peeled off. I had cut it off neatly. I'm going to stain up a couple pieces of veneer and attach them. Unfortunately, the grain is not a perfect match, nor is the color. This is cherry edge banding with one coat of Home Depot's water-based wood stain. This stuff, red mahogany, but on cherry. It seems to be the closest grain that I could find to match what was on the cabinet. Not perfect, but I don't know where to get something better. The staining is finished. It's a little darker, but that's okay. And the edge banding, unfortunately, it's only 3/4 of an inch wide, so I had to put on 2 strips. Not perfect, but certainly not horrible like it was before. Nobody ever shows the back of the set, but people who repair TVs like to see the back too. There was no place for a tube layout diagram on the inside, and besides, the one that came with the set was just wrong, so I've put it on the back.
We're in Albuquerque. Something important just came up. I better take this tape down to O'Brien, Thompson, and Kincaid. I should have listened to my mother and become a bookie.
The daylight 4000K white LEDs looked much warmer through the bezel and didn't look right next to the bluish-white CRT. Adding the blue LEDs along with the white LEDs looked much better, but bordered on purplish. It looked very mildly purple in person, but it was exaggerated on camera. Adding the green LEDs through a 47 ohm resistor neutralized the purple effect, but I wasn't entirely happy with it. I later changed the 47 ohm resistor on the green LEDs to a 16 ohm resistor. With that change, the color was very close to the bluish color of the CRT's phosphor. The red LEDs were unused. This video is coming from a DVD player through an RF modulator. There are two issues. First is the noise. That's the crappy RF modulator. The second is the picture is not right at the top. It almost looks like the deflection yoke is tilted, except it's not.
I'll do the talking. Good thinking. I'll just be the muscle.
This video is coming from an over-the-air transmitter. Fantastic picture and no noise. But as you can see, the raster is too low on the screen. The reason for this is the centering magnets. They're out of adjustment. Unlike newer sets that have rings concentric with the electron gun, this has 3 magnets that hang on brass strips off the yoke. The adjustment is time-consuming and finicky, and I haven't done it yet. I hope you enjoyed this video series on the Sylvania Halolight 21C509 TV. Please check back often for more interesting and unusual videos here on Mr. Brown's Basement. And please don't forget to let me know if you prefer long videos like this one or shorter ones. As always, thank you for watching.